Okay. Um, Let me, there's a few questions on the homework that I'll hopefully clarify. Okay, so if you have some more, happy to answer them. The first one, it, it's a little bit of a design problem. It says highest efficiency and smallest area. Excuse me. You can't get, those are, so what's the figure of merit we're really talking about here? So there's a little bit of ambiguity there. So what I'm going to say is that let W over L at transistor 3 be equal to W over L at transistor 2. So that's a constraint. So the problem should read with the highest efficiency and smallest area with W over L at transistor 3 equal to W over L at transistor 2. Okay? So I think then, because you can't get highest efficiency and smallest area at the same time, it's not possible. So with this constraint, that defines the problem, I think, makes it more clear. Another little, all devices should be in saturation. Of course, what we do is when we go into the most negative, most negative swing on the input, we bring M1 right to cutoff, right to the edge of cutoff. So all devices should be in saturation or cutoff, okay? And that's true for problem 2 as well, because push-pulls are always one of the transistors in cutoff and one's in saturation, right? So, or cutoff. Oh, here, I said it there. Okay. This business about you may choose your own value of DC level at the output. What that's, I think, was attempting to do is that when we define efficiency, we define it for a sine wave. You know, when I calculated the power into the load, I said it was V squared RMS over R load, okay, which is equal to V squared peak voltage over 2RL, right? And this is true for a sine wave, right? And so assume we're in a sine wave, and I think what this is, choose your own value of DC level. I think for the input, I guess what that was all about was so that the output would be around 0 volts. It's always true, what we assume is that the output needs to be symmetrical. It needs to be symmetrical around 0 volts, okay? So what they're saying there with that is that you assume that you can set the input so the output's at 0 volts, and it'll swing to +1 and -1. And you can choose whatever value of input voltage to make sure that you're symmetrical, that 0 you're at 0 and plus or minus 1. So that's what it's all about. Something I didn't say before. Let's say if you designed your circuit so that here's 0 volts, and the clipping point was at 0.3 volts in the positive direction and 1 volt in the negative direction. So if you put in a sine wave of 1 volt, or -1 volt, of 1 volt in size, what would happen is, of course, it'd go up and it would saturate on the 3 volt, and then it would have a nice swing in the bottom, and then go up and saturate and go down, right? Well, we say that's not acceptable, okay? Well, we'd say if you had this situation where you had +0.3 and -1 as the limiting points, the maximum output swing you could get would be 0.3 volts, no matter what the negative side is. So you notice when I did my little calculation in the notes, what I would do is I'd check the negative side for, that's set, let's say, by -IQRL. But since the swing has to be symmetrical and to be most efficient, then you would set the positive side equal to the swing in the negative side, so that you're designing for the symmetrical case, right? So any question about that? So I think what we're just saying is, you can, this comment about you choose your own DC level, just you can always make sure that you're biasing your output so it's around 0 volts. You can adjust the input if that's true. Okay. If the output was around, for example, let's say if you did it the other way, say V in can't be offset. You want to see what the output is with Vn at 0 volts, well, the output then would be negative, I guess, right? So then your swing would go, I don't know, like this or something like that, right? And it'd be offset. You wouldn't get the same output swing you could as if you had the output swing set so the output was at 0 volts. Okay. Okay, another comment. Plot V out versus V in for this. You can use SPICE to do these plots. You don't need to do those by hand. Okay. Plot V out versus V in. You can use SPICE to do these. Okay, in the notes, yes.
So basically, we can just say that V out goes from -1 to 1. Don't worry about it.
That's basically right. Yeah, that's what it means, right? You just worry about the V out. Make sure it goes from plus and minus 1, and it'll be whatever input voltage needs to do that is what will be used. Exactly right. In the class outline of how I'm doing grading for the homework, there is a statement in there which says you may turn in one homework late and will drop the one with the lowest grade. Okay? So a lot of you are wanting to use that late homework this week because there's a lot of midterms going on, I guess. And so so the question is, how late is late? Right? So let me define late. Okay, late will be defined as Friday discussion section, okay, because then we're going to put the solutions up right after that. Okay, so Friday discussion that equals late. Okay, right? All right, okay. And we'll drop the lowest homework too. So if you don't want to turn in at all, then you get one that's low, and I'll do that too. Okay, does that answer all the questions that we had with this? Any other questions with the homework? Okay. I'll try to get the news group to be a little more effective. Apparently it's not getting answered very rapidly, and I'll discuss that with the DAs. Any questions about material or what's on the midterm? We may get in the frequency response today. Probably likely will. That will not be on the midterm. Midterm material is up to basically this op-amp stuff, right? And so, any questions about that? Okay. So last lecture, I started talking about this telescopic op-amp and sort of bias swing of that. So let's continue on that a little bit longer, okay? In fact, your homework has this bias situation that I talked about beginning last week. So and that's kind of in the notes here. So you just have to be sure that, notice this, I should be careful here. This is not connected, right? Right? And this is connected. Okay. Okay. And what we're trying to do with this M9 is get the voltage at this point right here that gives us the high swing condition. The high swing condition is that we want to have WDSAT right across M2. Now, I had several questions. This business, sometimes I say, well, this needs to be WDSAT. What I'm saying there is, remember that VDS can be greater or equal to WDSAT, right? And that means it's in saturation. If VDS is less than VDSAT, then it's in linear. So we can't just ever say that this is exactly equal to VDSAT like we can say that in saturation this is equal to VT plus VDSAT, the VGS, right? I mean, that's true. If in saturation this voltage here has to be VT plus VDSAT. For this device, if it's in saturation, it can be equal to VDSAT, but it also could be equal to greater than VDSAT, like this equation says. So you can't know that this voltage is equal to VDSAT. Something else has to set it to be that. It can't be less than VDSAT and still be in linear region. And if it ever is less than VDSAT, then we know we got a different set of equations for this transistor, right? So since, yes, you can't see what? My hand is over it or something?
No, the words on the side you keep pointing to.
Oh, I see. Sorry. There. Okay. So VDS is greater than equal to VDSAT, and linear is VDS. So it's because of this greater thing, we can't just say that M2 is going to be equal to VDSAT. Because it can be greater than that and still be in saturation. What you got to do is find other things that set the voltage. What it sets it here is this VT plus VDSAT here. This is shorted, so that's the same voltage. Then we go down a VT plus a VDSAT of M8. So the difference between here and here is approximately equal to the difference of the VDSATs of M8 and M9. And what we'd like to do is to set this voltage here so that the VDSAT of that we set this voltage to be equal to the VDSAT of M2. And so we can do that by making sure that this is M9, that the VDSAT of M9, forgetting about the VTs, say the VTs have no body effect, let's say there's a difference of body effect here potentially, is equal to VDSAT of 8 plus the VDSAT of 2. You know, if the VT of 9 equals VT of 8 equals VT of 2. Right? And that's kind of what I do in the notes here. Right? Let's talk about that. All right. So that's what your homework's all about. Now let's talk about this problem a little bit here. What's wrong with this circuit? We mentioned it last time. The problem with this circuit is everything's stacked up. There's lots of transistors between the plus and minus supplies. In this age of small supply voltages, which are getting smaller, this is not very desirable. Okay, so this started happening. This problem that this circuit, great as it is, because it's so much gain in one stage. Boy, it's a super circuit, right? The problem is the swing problem, and particularly where the problem comes when it's the common mode problem. You take V input common high, take the input voltage on these two inputs to a positive, take it up high, then how far down can this voltage swing, right? Well, it can't go down very far if this voltage is way up high, because you have to sort of, this voltage, if this goes up, right, this voltage goes up, that means this voltage goes up, that means this voltage goes up, and that means we can't swing down very far in a negative direction here. So this circuit has a major problem with swing in the negative direction when the common mode voltage is high. Okay? Now, the question is there a way we can sort of help this circuit out? There is. And this is pretty tricky. All right. Let me the answer is this. What is that? So this seems like a big mess. Okay, so let's go through and let's figure out how we get from this to this. This circuit here, this thing called a folded cascode, notice there's cascode sitting in this term, and this telescopic thing is basically just a cascoded load with a cascoded driver device, right? I mean, M8 and M6 are just two cascodes over just a straight old differential pair. So this circuit and this circuit are very closely related. And what's really happening with this is we're doing something which allows us to get a better swing at the output. And particularly we get away from this dependence, having to worry about this common mode swing here. Okay? So how do we get from here to here? So first thing is, probably I shouldn't even have done this, but if we start right there and look at this transistor, here's the input V1 and V2. Here's M13. So this is a PMOS input, okay? So this is being NMOS. So really all I've done is flipped over. So this is the tail current source, M13. Here's the two input transistors. So this is just a flipped over version of M12 and M1, M2. Okay? So just forget all this other stuff. So this is, if we go back to our straight old differential pair, with a tail current source, with a current source load. This is basically what we have here without these, if we took these cascodes out, right? See that? Okay, right? So here's the current source load, right? Here's the two driver devices here. So flip that over. Here's the load. Here's the current source, tail current source, and here's the two driver devices. Okay? So we're back to straight old differential pair input. This is where the load would connect to normally. Maybe I just even draw this. So this goes off to a bias, and so I'm just saying all we have here to start with is this. Right? So this goes to some bias, right? So here's the current source load. This is M13. Here's M1. Here's M2. Okay? Get rid of all this other stuff. This is just a bias string over here. So this is just getting us the right currents. Now, the question, normally we hang the load off down here, right? We would put, like the, if we wanted to put in the good old current source load, right? Let me just draw it in dotted lines. Okay. We would do this. We would put, a current source load hung off down here. But now, we're going to do something different. What we're going to do, instead of doing that, we're going to go over into this circuit over here. So what is this all about? Okay? All right. The way to look at this thing is this. We're taking this lead here, okay, it's this wire right there, right? I'm bringing it over here. Unfortunately, okay. Here is this lead, that's this one here. We're bringing it over here. And then what M9 and M10 are, if you look at this, here's a diode connected transistor, and here's M9 and M10. Those are just two current sources. This is just a simple current source. So M9 and M10 are just, so let me just put two current sources down here. Okay, this is M9 and M10. Okay. Now, if we look what's we got above that, if we look at M7 and M8, and what are they just tied over to a bias point here? So what are M7 and M8 acting as relative to this output point here? What are M7 and M8? See what's going on there? So this is, let's say this is M8. This is M10 rather. So what's this guy here acting like? For this, relative to this point right here. Here's where V out's being taken, above M8, right? So here's V out. So what's M8? This is a V bias. So what is M8? It's a common gate. So what is it acting as? What's the other name for it? What? Cascode, right? That's exactly what a cascode is, right? I mean, this guy's acting like a cascode for this M10. So looking down to here, what's the output resistance I see? I see good old GM R0 squared looking down into this lead. So M8 is just a cascode of M10. Okay? So let's put that in there. So we just know what we got here. It's just a cascode device. And I'll put another one over here for symmetry. The second one's for symmetry. This goes off to a bias, V bias 2. Okay? Here we're taking our output. Now, what's above this? We see M3 and M4 good old diode connected transistors, and we see M5 and M6 good old diode connected transistors. So what's happening looking up in this direction? What does this look like? Isn't this just a cascoded current source? M6 and M4. Isn't this exactly the same as what we had right here? Here's M6 and M4. In fact, you can get the same numbers, right? M3 and M5. So this stuff right here is exactly this. So this is really the load, the current source load of this differential pair stage. And here's where the folding comes in. See, we started here with NMOS inputs, and we have the current source load sitting above it. Here I have the PMOS input, but here's the current source load above it. But it's kind of folded, right? It's sort of folded over. That's where the folded cascode comes from. All this stuff down here is just current source. So what the folding idea is that I take the output currents of M1 and M2, and let me not cascode it for a second. Let me just, so I can draw this a little easier. So here's our good old uncascoded current source load. So now, how does this folding work? So here's the really tricky part, okay? If we put in a differential input across this, right? Let's make it pure differential. Vn differential over 2 minus Vn differential over 2 on this one. So we're putting a differential current here. We're going to get a current out of here, right, of minus Gm times Vn differential over 2, and we'll get one here. It's Gm Vn differential over 2 on this side. Okay, so that's the current we're going to get coming out of these two transistors because of this differential input voltage we have here. Okay. Now, where does that current go? Here's the folding. Let's follow this little juice of current here, right? It goes cruising along here, right? Let me change colors. Multimedia. Okay, so here we go. So we come zipping along here. Can we go down in this direction? This is a current source. If it was an ideal current source, no small signal current can go into this current source. So it can't go that way. So where can it go? It's got to go up. Okay? And this is all small signal now, right? We're trying to get to a ground here, right? Okay? So this goes up. This goes up through this cascode. That's fine. So it keeps going up there. Then it hits this current, this diode-connected transistor, which is actually just this current source load. So that's going to get mirrored over here. So we see a minus, we see a Gm times Vn differential over 2. This is plus Gm Vn differential over 2, right? So it goes here, here, goes up through here, and gets mirrored over to here. Okay? What about this one? Here's minus Vn differential over 2 in this direction. So let's make it a plus Vn differential 2, and that means it's in this direction. Okay? This goes over here. So it's going in this direction, plus Gm differential over 2. Comes up to here, it's going in this direction. Can't go down into this current source, this DC current source. So it's another Gm Vn differential over 2 coming down here. What needs to come into here? This is sort of our I out. Well, I out's generally written this way. It's going to be minus Gm Vn differential. So what the folding idea is, we put these current sources down here. We folded the load from here up to there. Okay? And the current, because a small signal current has got to get to ground somehow, right? It's going to go where it can go. It's basically going to be a divider going on here, right? If you think about this, this has an output resistance of, let's say, R naught. Let me finish 1 second here and I'll ask you. And looking up to here, I see 1 over Gm. So it's kind of a voltage divider between 1 over Gm and R naught. So you can sort of see that most of the current's going to go upwards. Okay, yeah, question?
If it's a current source up on top also, why?
Up on top where? This one here?
Yeah.
So why?
I mean, you are calling that a current source.
Well, it's not a current, it's a current source load.
Load.
It's just like this, right? It's not, It's not a current source. It's not set to this current mirrors this current, right? But it's a current source load, right? Right. Then we cascode this, right? If we did this, if we just left it like this, the input-output resistance looking upwards would be what? Just R0, right? Looking down would be GM-R0 squared. So we'd only get an output resistance of R0. So we need to cascode this upper part as well. We put cascodes up there. Go off to another bias string, and we end up with this. Or we can do it like I did here, right? You could take us to another string, or you can diode connect it like this. There's a couple ways you could do it. So you got it? So see how it works? So basically it's just a good old differential pair. The trick is that you can fold a current like this, and what's kind of weird is, well, you think, geez, what's current going upwards? But remember, this is small signal, right? Right? Yeah.
So like the swing on the high part of VR is actually the same as circuit 2 that you showed, right? Like we don't gain any swing from the folded cascode on top, like from M4 and M6.
Right. Yeah, we haven't won there at all, right? Right. Where we've won is on the other direction, right? Because we got rid of this common mode voltage problem, right? Right. Right. So now now this is not a high swing, right? How high can this go in the positive direction as it's defined, as it's drawn right here? Well, how high it can go is it can go, well, what's this voltage right there? It can go within a VDSAT of that. Well, we start at VDD. This is a VDD minus VT minus VDSAT. This is down VDD minus 2 VT minus 2 VDSAT. This goes up. So this is at VDD minus VT minus VDSAT. So this voltage here has to stay 1 VDSAT below this voltage. So the maximum voltage it can be is VDD minus VT minus 2 VDSAT. We know if we have high swing that we should be able to get within a VDSAT of this VDD. We got the VT still sitting in here yet. So this is not biased in the high swing condition, right? How do we do that? Well, we could drop this down by a VT somehow or other, or there's some other circuits that I think I'll show you in a second. Okay. Similarly, going down, this is not biased in high swing in the negative direction either. So it's going to be also, I think, this comes out to be minus VDD plus VT plus 2 VDSAT as well in the negative direction. It also has a VT down here. So we need to do a high swing condition in the bottom as well. Then we can get to be within 2 VDSATs going up and 2 VDSATs going down, irrespective of what the common mode voltage on the input is. Yes?
I'm sorry. The problem with the telescopic op amp you said was because we didn't have good swing, right?
Swing in the negative direction, right?
In the negative direction, we didn't have good swing. But then you're saying this one also doesn't have good swing?
It has, okay, there's 2 levels of good swing here, right? Okay, so there's, first level of good swing is that we would like to be able to get, best swing of all is we add up, we want to have a cascode. We're not going to get less than 2 VDSATs no matter what we do if we got a cascode, okay? This circuit here is not in high swing condition, but we could use a high swing strategy here and get to within 2 VDSAT, right, of the positive. And we can get within 2 VDSAT of the negative. This circuit, even if we try to, this is actually a high swing. M9 sets this M2 into a high swing condition. We're 2 VDSATs from here to here. Unfortunately, we've got this voltage which goes up and down with V input common, so that really what kills our swing in the negative direction is the fact that when this goes up, this voltage goes up, even though it's 2 VDSATs to this point, but this voltage is getting fairly high, right? And that's really bad. So that's what this one gets rid of, that problem right there. This is relative to minus VDD. This one is relative to the voltage on the source of M2, which is actually V input common minus VT minus VDSAT of 2. Right? Yes.
The question is like, in this circuit, we actually just fold the input to like the other side, right?
Right.
So like when we come to the common mode, when we increase the input, we should also increase the voltage. I mean, like the VDS of M13.
M13. Okay, right here. Okay, right.
Yeah, we also like increase the VDS. So how come the voltage at um the source of M7 and M9 doesn't change?
Source of M, well, because look where it's connected. The gate of M7 goes over to M11 here, right? So this is a DC bias voltage, VB2. It's not connected anything to do with that voltage right there, right? So it's set by this swing right here. And the trick is we'd like to set this voltage as VB bias 2 so that, where should it be set at? We should set this voltage at VDSAT of 9, right? And this voltage then should be at VT of 7 plus VDSAT of 7 plus VDSAT of 9. So we should make V bias 2 have the voltage so that it's equal to this. And if we do that, then this voltage will be right at VDSAT of 9. This will be at VDSAT of 9. And this will be able to go as low as minus VDD minus VSAT of 8 minus or plus VSAT 8 plus VSAT of 10, right?
But like when we get input swing, the voltage at M13 will change. How come that doesn't change the voltage at the VDS of M9?
VDS M9. Okay, so you're worried about, okay, so let's take a common mode voltage. Which way should I go with this common mode voltage? Up or down? Up? What? Here our problem was when we took the common mode voltage up on M1 and M2. So let's worry about the case then. This is flipped over, right? So let's worry about the case when the common mode voltage goes down. Okay? It's kind of the same issue. So this voltage right here will track and start following this input common mode voltage going down. How does that affect our output swing? That's the issue here, right? When this common mode voltage went up, our output swing was damaged because this voltage, when it started to go negative, when this went up, this voltage went up, that meant this voltage went up, so our output swing was limited by what the voltage was here, and that's a function of this voltage down here at the source of M2. This folding separates the output stage from the input stage, so we're no longer sensitive to this voltage here in terms of what the output swings to. The output swings, it's limited by M4 and M6 and M8 and M10. So that's kind of the magic of the folding. I mean, that's what you're looking at there, what you're concerned about is exactly why this is an interesting circuit. I mean, it got rid of the fact that this voltage right here, which was all tied up in our output swing in this case, is now not involved in our output swing at all. So input common mode swing is one issue, and output swing is another issue. Here, input swing and output swing are very strongly coupled. Okay? Yeah.
When you're calculating the necessary voltages in the current bias M3, M4, M5, M6,
Yes.
are you assuming that they're all identical transistors?
Right now I am. Really what has to be the same is 3 and 4 have to be the same, and 5 and 6 have to be the same. But yeah, other than that, I assume this is matching this. There's that balancing, but there's lots of flexibility on, the other way. Okay? So here's a question for you. Okay, so let's, shall I go... Okay, so let's figure out what the DC currents are running in this circuit right now, okay? If we go back to this circuit right here, if this is, let's say, 2 ISS, okay, M13 is running 2 ISS. The question is, what's the current over in these transistors over here, the DC current? If this is 2 ISS, that splits between each of these, and I get ISS as well for each one of these. Now, what should I set these two current sources down here equal to? The folding currents. What should they be set equal to? Should I set them equal to ISS? Let's try it. Just let's set those, like to set everything equal, right? Told you to do that. Start off with everything being equal. If I set these two equal to ISS, I have ISS coming into here, I have ISS going down here. How much current's going through here? 0. Doesn't seem so good. All right, okay, so we can't use ISS there. If we want to keep this current and these currents the same, this will need to be 2 ISS. Then we have left over an ISS biasing these stages up here, and we're pretty much back to the same bias conditions that we had for the telescopic case then. We have the same currents in the loads that we did in the driver devices. But notice another feature here. We actually now can play around with having the loads and the driver devices, have different currents if we want. Is that useful? Might we like to do that? Why would you like to have the load currents and the driver currents be different? Any reasons? All right. Indirectly, but what's a more direct reason why this is a good thing to be able to play around with? What does the current in the driver devices do? What can we use it to improve that'll help our gain? If we put more current through the driver devices, what'll happen? What will improve? GM. Remember this. As I showed you here, big G sub m of this circuit is equal to what G sub m? It's equal to the G sub m of 1, or equal to G sub m of 2. So the G sub m of this circuit is actually set by the G sub m of these two input transistors. Okay? Remember how I did this? I mean, all this stuff over here is just sort of current steering, right? It didn't really add any more current. We had the current was all generated by these input transistors, just like it is in the telescopic. I mean, the currents out here are just set by the input transistor M1 and M2. Same thing here, even though it's folded and all that kind of stuff. Okay, so now, if we increase the current through M1 and M2 by, let's make this 3 ISS, okay? That will make the currents through here 2 ISS. That makes this 4 ISS. We suddenly have twice the amount of current through these, same amount of current in the loads over here, okay? So we can increase G sub m. So putting more current through the driver transistor gives us more G sub m, but it also allows us to have higher output resistance over here because we'll have lower currents over there relative to what we have here. In telescopic, we're sort of stuck, right? This current equals this current. This circuit, though, we can make these currents, this current through M4 and M6, this upper stage, have lower current if we want to. Okay? And we can make this transistor and its cascode all have lower currents. This one here, of course, gets even bigger. Okay? So that's the DC bias condition. What about making it high swing now? There's a bunch of ways to do it. This is not by anyone. You know, and I think Razavi gives several circuits for this. Here is a way to do the high swing of M3 and M5. Okay? So the question is, what we do here is this is a different strategy than we used here. So we're making this a high swing circuit. I'm taking this voltage right here, and I'm using that to set the, in fact, let me, I'll say it, and here I've got it all worked out. We have W over L's, let's call it, if I don't say what the W over L is, let's assume that it's 1/2, okay? All right? Okay, so, and there's two things you have to watch out for when you figure out what the WDSATs are of this circuit. Two things are changing. Currents are changing, and W over L's are changing, right? So the W over L, if this is 1/2 and this is W over L of 1, that means the VDSAT is bigger by a factor of √2, right? Right. But then the current here is twice the current here. We'll have to see what it is, right? So that also changes the VDSAT by another factor of 2, right? √2. So it's actually twice. The VDSAT of this guy is actually twice the VDSATs of these guys, right? All right. So, but look what's going on here. So we're taking this bias current, bias voltage here, and so this is just a cascode. So this is just a strategy for biasing up the cascode. So here, good old standard strategy, we're taking that DC voltage, applying it to M6. So this is good old common gate sort of circuit, okay? So this is a cascode for M4, so that's just kind of normal. What we'd like to have is this voltage right here at what voltage? VDD minus VDSAT of transistor 4, right? That's the best voltage we can have here, because that just puts this guy in saturation. That's the high swing condition. And that means this voltage in its most positive direction can be VDD minus VDSAT of 4 minus VDSAT of 6. So the question is this biasing strategy right here doing that for us? Okay? And so what you have to do is you have to look, and what sets this voltage right here is actually the voltage on this gate. So this gate voltage here needs to be VDD minus VDSAT of 4 minus VT of 6 minus VDSAT of 6. Okay? So that's what I have to have this equal to, right? And what is this voltage equal to? Well, let's see. This is going to be VDD minus VT of 14 minus VDSAT of 14. VT of 14 minus VDSAT of 14. So if I set, and that's what this voltage right here is equal to, which is this voltage right here. So if I take those two together, I see that VDD minus VT of 14 minus VDSAT of 14 needs to be equal to VDD minus VDSAT of 4 minus VT of 6 minus VDSAT of 6. No, yeah, right, VDSAT of 6. Okay. VDDs cancel. These all VTs, we got to worry about this a little bit, because this VT could be different from these VTs, so we may need to tie the substrates off on these things, right? Tie the wells. In the homework it said tying the wells to the sources, but that means just tying the substrate of this transistor to its source, so getting rid of the body effect. So that means VT14 would equal to VT6 if we tied those wells off, okay? So that means we have VDSAT of 14 needs to be equal to VDSAT of 4 plus VDSAT of 6. So VDSAT of 14 needs to be equal to VDSAT of 4 plus the VDSAT of 6. And we've done that by making this have twice the current and 1/2 the W over L. That's how. And so if this, so that's the strategy. So twice the current here from these here, plus WL being 1/2 of these, makes this condition true. Okay. So what's this little bias business going on here? Why do we have this connection? This is kind of a nice little, this is a high swing bias circuit. It's a lot nicer than the one we had before. Remember, before we had this, in fact, we have it here. We had that little source follower with the battery and all that kind of thing. So I'm claiming this is also doing high swing. But it's a lot simpler. It's just it's the same number of transistors, no source follower with a little battery, right? So what's this connection for? What is it doing? Why do we need it? If that connection's not there, what sets the voltage on this node right here? on the drain of 5 and the drain of 7. There's nothing that sets that voltage, right? It's a really high gain condition. Basically, what do we normally have there, right? What we normally have there for like here we have diode connected transistors. In effect, this is a diode connected transistor. We're taking that gate voltage and we're bringing it up here and using it to bias this point. And what is this voltage equal to? This is at this voltage right here is equal to VDD minus VT of transistor 3 minus VDSAT of transistor 3. And it turns out, you know, we got a nice little VT3 here that we have. What do we need? This voltage, this VT, is enough to make sure that this device will stay in saturation. So this voltage here with this VT brings this voltage up high enough to keep it in saturation. And you can sort of see I did it here. Delta V's are sort of a nominal VDSAT, right? So delta V equals VDSAT of 4. These two V, let's call that VDSAT, delta V of 4 and 3. So I call that delta V. If you look at what the voltages that we have at this node right here, it's VDD minus VT minus 2 of these delta V's, which are the VDSATs of 3 and 4. VDSAT of transistor 13, for example, is equal to it's equal to 2 of these VDSATs, right? Okay. But you can sort of see that what's happened is this bias swing string here sets this voltage at VDD minus delta V. So that puts this in high swing condition, as well as this one in high swing condition. And then this one, all I need is another VDSAT across M5 in order to have this in high swing condition. But just by connecting this up, I get a VT plus a delta V. So I get plenty of voltage to put this guy in saturation. So it's more than enough. But this doesn't have to be right at the hairy edge, you know. It might be a problem if we really start squeezing down the supply voltage because we've got more than enough voltage across here, but this isn't where the output's connected to, so this is all right. Whew. Go back to slide 19. Yep. And scoot it down. Is that scooted? Okay, big picture stuff here. So what's going on? What did you just learn? And let me just finish up a little bit on the lower side. What did I do? Here's a source. M15 and M16 are a source follower, right? This right here. So this is just that little battery. So this is the old VT plus VDSAT battery, M15 and M16. So we added that in, right? See, there was M15. Well, it's even there. Where is it? My earlier. See, in this circuit, I take M11 and I just tie it directly over to M7 and M8. That's not the high swing condition. Here I take M11, go through a battery, and then connect to 7 and 8. So that makes it so using this M5, 15, and 16 are for the high swing bias of getting M7 and M8 lower. So this is connected to just minus VDD plus VDSAT of transistor 9. So that's what this drops the voltage to do. So we're using a source follower to set the high swing on this lower cascode, and we're using this simple little diode connection strategy up here to set the high swing on the upper one. So this is a high swing folded cascode with high swing on both plus and minus. So that means we're going to swing within 2 VDSATs of the positive supply and 2 VDSATs of the negative supply, irrespective of what the input common mode voltage is. So this is a much better circuit. And we get the cascoding, so we get output resistance is going to be equal to GM R0 squared. We get input gain is GM, so the gain of this thing is GM R0 squared, GM squared R0 squared, just like the telescopic. With a little bit of loss because of this current, because of this, what happens right here. Remember, we got a little bit of current division going there, so that hurts us a little bit. Break time. Don't need it, do you? Eyes are eyes. Mm. Yep.
Two questions. One was, why do you need this up here?
That's the current source. That's the tail current source, right?
But I thought you have a current source down here.
Tail current source, right? It's this guy.
Why would you need two current sources?
For the common mode range, common mode swing, right? This is just that current source.
Yeah, on 13 is 12, right? So what's this? Why do you need this current source? Just
For the folding, just for the folding.
Another part
It
is,
provides current for this stuff, right?
okay. Well, what else? You said you have a little bit of loss right here. What do you mean it's loss?
Remember I said that this current I said all that current went upwards into the output eventually.
Right.
Looking down it sees R0, looking up it sees 1 over GM. So there is a division between 1 over GM and R0 here, which loses a little bit of current, a little bit of gain. GM is reduced a little bit by that current division.
It's not a perfect current source?
Yes, because it's not a perfect current source, right? If this is a perfect current source, then we lose nothing through here. But it's really R0, right?
So you lose a little bit of the current, so the ROs go down?
No, because the big GM will be reduced.
Big GM is only dependent on this GM, though.
Okay.
So why does it matter?
Okay, it's that plus, as modified by my final statement, that if all of this current went here and then all of it went out to there, then it'd only be dependent on that. But in actual fact, what it does, it hits here, and it'll be a current divider between 1 over GM this way and R0 this way.
Current divider between 1 over GM and 1 over R0. Okay.
Right. And this is an
Yeah,
R0.
that makes sense. Current divider. So that's our big GM. Our GM is
Big
the
GM.
current divider of this GM.
It's the GM of this things plus this current divider here of between 1 over GM looking this way and R0 looking this way. Remember how you do it. You short this, right? And that shorts this node here. So then so looking up into here, it's truly 1 over GM. And looking down here is R0. So it's just R0 over R0 plus 1 over GM is the reduction.
That's the reduction factor right there?
Yep.
Sir, can you explain again why you need to connect it like this?
Let's say we didn't connect that.
Yeah.
What's the voltage on this node? What sets it?
Nothing.
Nothing. Well, so something sets it, right? So it's some little mismatch of currents. I mean, we then have to bias this up. What this actually does, you got to look at this. It's like a diode connected transistor, right? See this, the current here equals the current there, right?
Yeah.
And so we sort of place this in the center there. It diode connects this transistor, right? But also provides a voltage on this side here that actually sets the drain voltage of this.
So even if you don't even if you don't connect it, you still have the high swing, right?
Yeah. This sets the high swing, but I got to somehow make sure this transistor is in saturation.
So it would go out of saturation?
Potentially could, pretty easily. Yeah, because this is a very high gain node right now, right? And so there's some mismatch of currents here and currents here would be setting this voltage on this node, and it would be pretty tough to match all those currents and small VT variations. And
This is just to limit the
Set the-
upper swing on this.
well, there's no swing here hardly. This is like a diode connection. It's just like a
I mean, this connection limits the swing on this node.
yeah, effectively. Yeah. Set the voltage there.
Sets voltage on it.
Yeah, reduces it down to
To keep this in saturation.
looking up into here. What do you see? You see the diode connected transistor. So looking up this way, it's 1 over GM. So there's no gain.
Connect transistor here.
Well, look at it. This current here equals this current, right?
Okay.
So tying this to here is almost the same as tying it to there, right? Right? Because the current through here is the same. So as far as the current here, so that's like a diode connected transistor, right?
Oh, yeah.
But I'm putting it up here. I use it does double duty.
Is it 1 over GM3 plus 1 over GM5 then? Or 1 over GM3 plus GM5?
Well, looking into
Diode connected transistor, right? The
well,
resistance
actually,
is
what's
1
set?
over GM.
Yeah, but actually not really, because this current equals this current no matter what. So that the current through here is set by VGS of M3. So I look into here, so I change this voltage, I change VGS of this, and that's what sets the current. That's the current I see here.
So what's the total?
So M5 doesn't do anything. So M5 is just like it just,
So it's still, this whole thing, resistance, is still 1 over GM3?
yes.
Oh, wow.
Because remember, it's the current in of the current out of M5 is the same. Okay. Let's finish up. I had a little more discussion just in our little right there. Let me just look at this M3 M5 thing a little bit more, just to show you. It's a little bit of a weird connection, right? Very handy. What's going on there? Let's look at this right there. Let me just draw it out again. Here's VDD. Here's M3. Here's M5. Remember, this is going off to some bias voltage, okay? And this is going down effectively into a current source down below here. Let's this is a current source here, and this is cascoded, so it's just a current source looking downwards. So effectively, we got a current source down here. So what is this thing doing when I tie this off here? If you sort of didn't have this transistor here, what is this? And this is going over. So this connection is really just a diode connection of this current source load. Okay? So I could have done it right here. But I sort of made it do double duty. Okay? I put this other transistor in here. The current here is exactly the same as the current here. Right? So when I look, let's say I look into this and I want to figure out the resistance looking into this node. When I change this voltage, I change the VGS of this is M3. So the current I see flowing here is just basically GM times, VGS of 3, which is equal to, if I call this V test, is going to be GM times V test, and this is what I test is going to be looking into here, right? So, and this is transistor 3. So what is the resistance looking up into here? It's just 1 over GM3. The fact that this transistor is here, because the current here is exactly the same as the current here, it does nothing with respect to what I see looking into here. So this is just a good old diode-connected transistor that happens to have this transistor stuck in the center of it. But it's handy, because this voltage now sets the voltage on this node at VDD minus VT minus VDSAT, and that's just what we'd like. That's plenty enough voltage. I mean, this voltage, let's say, is, because of this bias, let's say this is set at VDD minus VDSAT. So I have, at this voltage, it's VDD minus VT minus VDSAT. So I have an extra VT here to keep this voltage, and long as the VT of this transistor is greater than the VDSAT of transistor 5, then this device is in saturation. Right? So it's just you had diode connect this somehow. If I tied it down here, then I have to figure out another way to set this voltage, and so this kind of does two things at once. Okay? And it's better than diode connecting two of these together, right? Because then we got two VTs plus two VDSATs. So, yeah.
M5 doesn't do anything except add the cascode. You need to be the cascode.
Yes. Yeah. On this side, it doesn't do anything. What it's for is on the other side, and it needs to balance the two circuits. Okay. All right. Really useful circuit. Folded cascodes, because it's high swing, it's one stage. I mean, it's really one stage here yet, though we have this little bit of current. Let me just finish up what I just said about looking down to here. What do we see? Looking down here, we see R0 of 10. Looking up into here, when I'm figuring out what the big GM is, I short this, right? And looking up into here, what I'll see 1 over GM8. So when this current comes over from this output from M2, what I see is Gm over 2 times Vn differential, right, times R010 over R010 plus 1 over Gm8. So this is that little reduction I see in the big G sub m because of the current division going on because of this folding. But it's not too bad, right? 1 over Gm and R0, it's not too, it's worth it for the big swing we get here. So that's the only effect. It's not like a, now there is, as we'll talk about pretty soon, this is kind of 2 stages. You have a stage here and you have a, like, looks like a folded stage here. But since this is such a low impedance, this is at 1 over Gm, right? This doesn't give us any stability problems. What we have to worry about stability problems are multiple stages that have a high output resistance, like R0, like 2 cascaded common source stages. Because this is a really low resistance, the frequency response of this stage is really high frequency and it doesn't cause any problems with our stability. We'll talk about that a little bit later. A little foreshadowing. Any questions about that? And you got to watch out. I mean, here's, on these kind of stages, going up and down, what will happen is, here's the really high gain region. And if you look at it not on the right scale, this thing will look, it'll look like a sharp line, right, because the gain's so high. But if you blow it up, now I'm going between plus and minus 1 millivolt, you'll begin to see this is where that upper transistor is going into linear region, right? This is where M6 is going linear, right here, and this is where M8 is going linear, right? And the gain's dropping. Here's where everything's in saturation. Here's where the gain's the highest. Right? Okay, so you got to watch out on your slopes. And so sometimes you may get yourself biased up in these range here. So why is my gain so low when I do these Cascode things? If you don't look in the right scale, you may have yourself set in a condition. I mean, this is a big swing. This is plus or minus 5 volts, right? So there's a lot of room in the center here, but you may have a much narrower room. You have to bias these things up at. Make sure you have the high gain. Okay. All right. So here's just an example of the high swing improvement. This is before and after high swing. In high swing, you get little WDSAT, and here's what it was before. Now, if this was not between plus or minus 5 volts, the difference between here and here would be much more important, right? Okay. Is that it? We're done with that. Any questions about DC operation, op amps, DC gain? Because we are now moving into a new era, a new world, right? And you're going to really enjoy. This is good stuff, right? Making your circuits real, finally, right? This frequency response, not having that as part of your circuit design is throwing out a really big step, right? And so now we get to build circuits that are, kind of, all the constraints we do your next design problem will have frequency response in it. And now you won't be able to go to 1 picoamp of current and get gains of 1,000,000, right? Because you'll find the circuits will run too slow. So now you're becoming rail designers. Okay, so any questions about this other stuff? Material, as of 10 seconds ago, will be on the midterm. Material starting here will be on the final, right? Not on the midterm. So any questions about the other stuff? I'll do a review for the midterm next Friday, Wednesday, I guess. Probably do Wednesday.
Wednesday.
Yeah, do Wednesday. Okay, I'll go over Wednesday. I'll just go through what I think. I'll just go through and tell you what I think is most important. I've been doing that all along.
How many midterms do we have?
How many midterms do we have? 1 midterm, fortunately, right? So so it'll be the lecture notes have all the exams and everything on it, and all the homeworks and everything. So I'm pretty much got that updated, so you can believe those numbers. I'm going to try to stick with what I have in the lecture note schedule.
When are you going to do the review?
Wednesday. This Wednesday. 1 week, so you have 1 week. Right. So midterm's a week and a half from now, right? It'll be in Bechtel Auditorium, not here. Pardon? Same time. It'll just be in class. So it'll start, try to be there on time. I will start, it'll be 1 hour and 20 minutes, okay? So, but let's try to use all 1 hour and 20 minutes, okay? We'll start right at, whenever we usually start, 11:10, right? And so we'll start right at 11:10, we'll stop right at 12:30, okay? So try to be there, right? Sit, well, I'll tell you this before, but I'll say it now. Try to sit apart. It's a big auditorium, so try to get away from each other, okay? And try to sit right behind the person in front of you, not a little bit to the side, okay, right? I know people wouldn't want to look, but you just, you know, yeah, but you can work at it a little bit. I mean, there's right behind, and there's you can do it. I have trust, right? But try to keep away from each other. Please, just do it. It just helps you. I know you wouldn't do anything that we all wouldn't be proud of. Okay, so we're ready for the new material. Okay, so frequency response. So let me just summarize what we've done. We've done DC analysis, small signal gain, DC biasing, and we'll summarize that in your midterm. And that was your first project was about. Next step is frequency response. We will now add in parasitic capacitors. And we'll also talk about, I'll probably work in some inductors, which are not parasitics, inductance that we add on our own so we can do tuned circuits like we do for RF design. So I'll talk a little bit about that. But basically we have frequency-dependent components, inductors and capacitors, that we're going to add into our circuits now, okay? And after we finish that in itself is interesting because now we can do circuits that have frequency response. And then we'll add in feedback. And we'll analyze feedback just as alone, without any frequency response or anything else to start with. Then what we'll do is we'll add feedback plus frequency response, and that gives us stability problems. And that'll be the next thing we'll go through. And then that is pretty much all of the hard material. Then there's some more transient response stuff we deal with. Like if you put in a fast changing signal, what happens? These circuits go nonlinear in that regime. And so we'll analyze that a little bit, but that's fairly straightforward. And that'll be the rest of the year. That'll be it. Okay, so it's frequency response, feedback and frequency response, which is stability, a little bit of nonlinear response, slew rate, things like that. And that'll be it. So that's what's in store for the next 4 or 5 weeks, or 5, 6, 7, or 8 weeks. Okay, quick review of how we analyze frequency response. What we will do is use something called Bode plots. Okay, hopefully you've seen this before. What we're going to do now is our change of point of view is that before where we thought of our circuits of being small signal variations at basically very, very low frequencies, okay? We assume the frequency is nearly 0. We are now going to think about what's driving our circuits, our 2 ports, as being a sine wave. A sine wave characterized by a frequency omega. So it's sine of omega t. And what we will now do is figure out transfer functions, whereas before we had V out over V in, not as a function of frequency, only as a frequency at omega equals 0, we will now calculate it as a function of omega, or frequency. So what happens to our circuit as we change the frequency? Well, for any 2-port or any circuit, as you change the frequency, what will happen, typically, is it goes in, and there's an amplitude and phase. So this is amplitude A, and phase is where it crosses 0. It's the sine. So if we really have our omega t plus theta, and theta is the phase shift that we see with our driving signal. Well, let's assume that we drive with theta equal to 0. Okay, so we start off with sine of omega t as our input source. What do we get at our output? And let's say this is A. What we get at the output is something that is a magnitude of h of omega, an amplitude variation times the A, which is the original input signal, times sine of omega t, something at the same frequency, that doesn't change, plus a phase shift, which is a function of frequency also. So we now have two things we have to calculate. We've got to calculate this magnitude change. So what comes out the outside here is something that's maybe reduced, it may be increased in amplitude as a function of frequency. Depends on if you have inductors or not. So the amplitude will change and the phase will change. In other words, where it crosses zero. So this phase shift. You may think, wow, why do we care about this phase shifting? That doesn't seem like too important, something to deal with. That's the stability problem, is all to do with phase shifts, okay? All right? So stability is why we have to worry about this theta thing. So we will calculate amplitude and phase just like they're equally important. It's not very important, actually, if you just have an open loop amplifier. If we just had like a common source stage, and some current source, and we calculated the input to output relationship, the phase shift wouldn't be very important to us, okay? It's when we close the loop, we put feedback in this thing, the phase shift becomes very important. So we will calculate that because it's going to be important to us in the future. How do we calculate these magnitude and phase differences? Well, we work in the complex domain, and so we calculate something which we will call V out H of omega, which is equal to, as I've shown here, the ratio of V out of omega versus over V in of omega. Okay? Why do we use sine waves? The real reason we use sine waves, there's all sorts of mathematical reasons. Bottom line, what it comes down to is when we put something in at frequency omega, it comes out at something frequency omega, right? We put a sine wave in, the only changes are is this phase shift and magnitude change. If we used any other waveform, a square wave, anything else, it wouldn't be true. It wouldn't come out just a phase shift and amplitude change. It'd have a much more complicated variation to it. So that's basically the reason. It's a fact. So sine waves are very special. They're basically eigenfunctions of the differential equations which describe these linear equations. Okay, so it's a really fundamental reason why sine waves are so important to us. Now we'll just treat it very pragmatically and know that if this goes in, this comes out, and we'll just worry about it. But it's really a very fundamental difference, okay, than any other waveform. Okay, so let's calculate this transfer function, V out of omega versus V in of omega, for a simple RC network. Okay, let me just go to drawing this. And the way we do this is we know that a very important simplification is what we call phasor analysis. And you all should have had this, okay, in 105 or 120. I'm not going to ask you if you did because I just know you did, okay? Bottom line, what you got to remember is that we talk about impedances instead of resistances now, because we're now going to add capacitors and inductors. I'll start with capacitors right now. Once we add capacitors, how do we sort of deal with them and in terms of our circuit equations and our analysis? If we go to impedances, we can say that the impedance of a capacitor is equal to 1 over j omega c. Impedance of a resistor is R. Impedance of an inductor is j omega L. So the impedance of a capacitor, it goes lower and lower as you go to higher frequency. Impedance of an inductor goes higher and higher as you go to higher frequency. It goes higher and higher as you go to higher frequency. In other words, if you take limits, and this is something you should do quite often, in the infinite limit, infinite frequency limit, you can quickly look at it. What happens? A capacitor becomes a short circuit. So in other words, V out over V in at infinite frequency will be equal to what? 0, right? Because this will be just shorted to ground. What is the gain of this circuit at 0 frequency? 1 over j omega c. A capacitor comes an open circuit at 0 frequency. And that's the limit we've been working in up to now. So all the capacitors are just gone. So our output gain will then V out over V in be equal to 1. So for the two limits, we can calculate just very quickly. It starts off with a gain of 1, and it ends up going to 0 at very, very high frequency. Now the question, what happens in between? The way we can figure that out, we use this impedance calculation. And once we have impedance, we can use the good old KVL and KCL we always have worked with in the past. So what is this? Is this simply a voltage divider? Voltage divider between C, 1 over j omega C, and R. So h of omega, which is equal to V out over V in of omega, is simply just this voltage divider. It's V in of omega times 1 over j omega C over R plus 1 over j omega C. Simple voltage divider, right? Between here and here, right? V out equals V in times this ratio. We can multiply top and bottom by j omega C, and we get 1 over 1 plus j omega RC. So this is actually something, it's in a very standard form. And we'll get everything in this form. We have 1 over 1 plus something, okay? And what we will do is if we plot this, what we will find is that it looks like this. This goes out, and at the frequency 1 over RC, if this is omega, and this is magnitude of h of omega, at the frequency where we have omega is 1 over RC, you can see what happens here. This is be 1 over 1 plus j then, because omega becomes 1 over RC, I mean this is just 1, these two things cancel out. So at that frequency right here, 1 over RC, we end up with 1 over 1 plus j. And that's what h of omega is. So this has the phase shift in it as well. So what's the magnitude of h of omega? The magnitude we have to do is we have to take is equal to h of omega times h of omega complex conjugate and take the square root of all of that. So we take this times its complex conjugate, and what do we get? We get 1 over 1 minus j times 1 over 1 plus j, so this would be 1 over 1 plus 1, okay? Take the square root of that, and this seems up to be 1 over square root of 2. So at the magnitude of h of omega right at this point is at 1 over square root of 2, 0.707. If we express that in dB, 20 times the log of magnitude of h of omega, this is the dB of this thing, this is equal to minus 3 dB. So we call this the omega 3 dB point. It's the point where the gain is dropped by 1 over square root of 2 or minus 3 dB. So we often write this as 1 plus our transfer function, we often write as 1 over h of omega, 1 over 1 plus j omega over omega 3 dB. Omega 3 dB for this case is equal to 1 over RC. So this is a single pole response. And what we could also have done, instead of working in this Fourier transform domain, we could have worked in Laplace domain. Now here's a big step, and I'm not going to be very rigorous about this, but if we went in and calculated the Laplace transform of this same circuit, then instead of using 1 over j omega c, we would use 1 over sc, and s is the Laplace transform variable. Why would you do this? This allows us to calculate the response to any arbitrary waveform, okay? Though we don't ever do that hardly. We only worry about sine waves. But if we wanted to, we could calculate the Laplace transform of this thing. But we kind of know how to get to it. H of s is going to be equal to 1 over 1 plus s RC for this circuit, okay, right? And we can define this, the pole of this Laplace transform is where this thing goes to infinity. That's a definition of a pole. Where does this thing go to infinity? When s is equal to minus 1 over RC, this thing goes to infinity. So we call that the pole. So we can write this just like we write 3 dB point for Laplace transform, like as 1 plus s over sp, okay? Or 1 minus s over sp, I guess, actually, right? Yes. So when s equals sp, this thing goes to infinity. Okay. So this is kind of this is the standard formula for Laplace transform variables, and we'll often plot this, and I'll talk about why this is useful to us. But in the Laplace transform domain, we have sort of the j omega axis. Remember that h of omega, is equal to h of s evaluated for s equals j omega. That's exactly how you get between the Laplace domain and the Fourier transform domain. Okay. You take s equal to s j omega. So there's kind of a j omega axis. There's a sigma axis, which is the real axis. And if I plot this SP equals minus 1 over RC, where is that? It's right here, and it's at spot 1 over RC. So this is the plotting of this pole in the Laplace transform domain. This will be useful to us, and I'll tell you, and I'll work through why it's useful to us in the future. But basically, this is how we analyze. This is what we're going to do to analyze these frequency-dependent transfer functions. See you Wednesday. Well, review it. We don't do much Laplace.